¿Qué micrófono se va a usar? Disculpe. Que normalmente colocan, usually they have
That was Ronberg. Okay. You will meet him. It's going to be exciting. He's not a concrete guy at all. I think it's going to be great. It's totally different from Ron, but I think he's going to be a great manager.
¿Se podría meter en uno de sus bolsillos?
Sí, sí, cómo no.
¿Sí? ¿Está prendido?
Oh.
Me gusta este. ¿Dice el apuntador?
Sí, sí.
Pues muy buenas tardes, tengan todos ustedes muy bienvenidos a este evento, esta conferencia del doctor Antonio Nanni, quien es un querido amigo de mucho tiempo atrás. Actualmente además es el presidente del Instituto Americano del Concreto, es el presidente número 100, aunque él tiene como la mitad de edad de eso. No es la edad de él. El doctor Nanni es profesor en la Universidad de Miami, en donde él ha iniciado una carrera muy interesante de utilizar materiales compuestos que se denominan, que son materiales no metálicos, fibras de vidrio y otro tipo de fibras, para reforzar las estructuras de concreto. Y gracias a su liderazgo, a sus contribuciones, pues el Instituto recientemente publicó el primer reglamento de construcciones en donde se pueden diseñar estructuras de concreto, pero ahora con barras de este tipo de materiales, no con barras de acero de refuerzo como usualmente estamos acostumbrados. Entonces, el día de hoy pues viene de visita a México, viene de Hermosillo, Monterrey, va a estar aquí en la Ciudad de México y posteriormente va a Mérida, como parte de esta gira que como presidente de la ACI hace a diferentes países, así es que para nosotros es un privilegio que haya dado un espacio para estar en el Instituto de Ingeniería. Tenemos conectado a un grupo de personas a través de las redes sociales del instituto. No sé cuántas personas tengamos conectadas ahorita, pero seguramente serán muchas, Tony, de manera que será muy interesante no solamente que te escuchemos aquí y aprendamos directamente, sino también lo hagan nuestros colegas a través de las redes sociales. Y el día de hoy en la tarde va a dar otra plática, que es de alguna manera complementaria a esta, en el Colegio de Ingenieros Arquitectos, con la sección del ACI de la Ciudad de México Centro Sur. Entonces, pues muchísimas gracias por estar con nosotros y él nos va a hablar justamente de los desarrollos, las aplicaciones en el campo del uso de las fibras o de las barras no metálicas como refuerzo de estructuras de concreto. Muchas gracias, muy bienvenido y adelante, por favor.
Gracias, Sergio. El placer es mío. Me gustaría hablar en español, pero no puedo. Mi español es mejor después que tomo un poquito de tequila y ahora es temprano por eso. So I can switch to English, and actually I typically prepare my slides with half in English and half in Spanish, but today, because there are many students, you need to practice your English, so I'm just going to stick to it. This is not supposed to be a typical lecture. This is supposed to be a conversation, so if you see something that you like to ask me a question about, I'm at your disposal. So this is thanks to Professor Alcocer for this invitation. Is again great. I've been around, I've seen now 3 cities. This is my second time in Mexico, but it's very, very exciting. The presentation that I have today is really broken up into 3 parts, and it's going to be a little longer, but Sergio gave me permission to entertain you if you wish. So the first part is really letting you know about ACI, what are we doing there, some exciting stuff, and the code in particular, right? And then I want to show you some field applications, because to talk about innovation without going into the field, without having real application, it doesn't make much sense. And then because Sergio asked me, I show you some of the research work that we're doing at the University of Miami. And by the way, I'm in a recruiting mode. So if you're interested in doing a PhD in the United States, we would be, okay, he's not looking at me, but he knows that I'm recruiting students. And so please feel free to contact me. And I will present you very quickly 3 little projects related to FRP. So the topic of today's discussion is really composite, and in particular composite rebars. What are they? Many of you might know what they are, but I'm just going to give you a few slides to remind you. These materials are made of fibers and resin. The fibers that we cover in the code are glass of the type ECR, corrosion-resistant E-glass, electric glass. And the resin that we cover is really vinyl ester of all the thermosets that are available because of the durability. The bars that we use in the code, because this is really what we're doing in ACI, follow the specification of ASTM D7957. So we have material specs that help us in defining what is the quality of the bars. The type of bars that you see in this picture kind of are unusual in the sense that if you think in terms of steel, the steel external surface, the steel rebar's external surface has been standardized. This is not the case for FRP. So they are all different depending on the manufacturer. And the reason for that is really to give you good bond with the concrete. Without stress transfer between concrete and reinforcement, you don't have reinforced concrete, right? So this is the purpose. The quality of the bond may not be as good as in the case of steel, primarily because of the stiffness of steel compared to FRP. I'll get to that maybe towards the end of the presentation. So the types of surface deformation could be helically wrapped, ribbed, sand-coated, grooved, all these different things, but ultimately the purpose is the same for all of them. In terms of quality assurance, and if we follow this ASTM D7957, we run tests that are different from the one that you might see in the laboratory. And I'll give you an example of only one, this E2160. This is to measure the enthalpy of polymerization. What the hell are we talking about here? What we need to do is to make sure that the resin is fully polymerized. If we don't reach at least the 95 to 99% polymerization when the bar exits the pultrusion machine, we will not have the durability that we expect. So this is one of the tests that we run, and a specification of the standard tells us what is the range that is acceptable. The D7957 tells you many things. Here I simply have a table to indicate that one of the interesting items is we define the maximum and the minimum size of a rebar depending on the denomination. So here you see in yellow an M16, a number 5 bar according to the US standards, and you can see here what is the nominal diameter, what are the cross-sectional area, minimum and maximum sizes, and then what is the guaranteed ultimate capacity. And this is measured as average minus 3 standard deviation. So very, very stringent requirement. So one of the issues that came to the table in the 90s, before many of you went to school, right? Maybe you were in primary school or even in kindergarten, there was the question of durability of the glass as a fiber, because glass is not really performing well in an alkali environment, like, concrete typically has a pH of 12 and above, right? So the issue of durability was brought up and discussed many, many times, but we have finally demonstrated, not only with accelerated tests in the laboratory, but also in the field, that this durability is there. And the primary reason not only is because the quality of the fibers has improved, we now use ECR glass, is also because of the protection that the resin affords, okay? So in this project that actually was sponsored by ACI itself, we collected samples from bridges that had been in service already for 15 to 20 years. Here you see the various locations. All of them but one, I was involved in their design, by the way, so it's something that I knew. And then we selected samples, we brought them to the lab, we tested, and we saw that the signs of physical chemical deterioration was minor. So we know for sure that if we design with these materials that follow the ASTM D79 specs, we can assure a life of the structure, a service life of 100 to 120 years. So this is a significant jump from what we do with conventional structures today. So now this is the biggest thing, and this is what we are proud of in ACI. We have developed, all of you I'm sure are familiar in one way or the other with ACI 318, because this is the building code for reinforced concrete, right? Reinforced and pre-stress actually. But now we have a 318 dependent code. That means this is kind of the twin of it. But look at the title, is reinforced with the GFRP bars. So now in the United States, since September the 2nd, 2022, so not even a year, we have the ability to use these materials in buildings. We have done it in bridges many, many times because in 2018, we issued the first version of the ASHTO design specs. So the bridges were ahead of the buildings, let's say, a period of 5 years at least. Why? Because in bridges, the issue of corrosion is much more, let's say, predominant, and also because in bridges you can identify the owners very rapidly. So this for us was a great event, but not only it's been issued by ACI, but 2 weeks after this became an official document of the Institute, it was adopted by ICC, the International Code Council. So starting next year, the model code, IBC, the International Building Code, will allow the use of GFRP bars. And if I understand correctly, and this is also an appendix in the building code here in Mexico City. So I'm very excited, and I want to see the next building. Actually, Professor Alcocer has promised me that next year he will design a building here with FRP only. So let's see if he can keep his word. Well, the purpose of the code is to ensure safety, right? So this, like, if you read 318, is the same reason. Provide minimum requirements, both in terms of materials, design, and detailing, okay? The devil is in the details. So this is really what, maybe I should have also emphasized, you see here, for GFRP bars that conform to the requirement of D7957. And by the way, 2 months ago, ASTM issued another spec for GFRP bars is 8505, D8505, that covers the new generation of bars that have a higher modulus of elasticity. Because I will tell you in a few minutes, one of the things that you could consider a weakness, but is not, is the lower modulus of GFRP as compared to steel. So the code is developed, obviously, this is a pitch about ACI. We are a technical organization. We are not a trade association, so we work by consensus, right? So this went through all the steps within ACI and covers all the topics that are listed here. If you're familiar with 318, this is just a repetition, okay? So you have the ability now to design a building, the entire building, from the foundation to the roof with these materials. One of the things that might not be exciting in Mexico City is the statement that as of today, because these materials are linear elastic to failure, so they are not like steel, which is a blessing of God, a material that's linear elastic and then plastic, then we have limited in the code the use of these materials in seismic zone category A. I'm not familiar with Mexico, but if you have 4 categories as we have in the United States, especially in C and D, you cannot use this material yet. But I think this is a topic of research that UNAM has to cover. If you want to be in a leadership position in new technology, this is an area. And actually the folks in New Zealand and in Europe are starting, so you better move quickly if you want to no, I think this is a topic for another day and another discussion. How can you address seismic safety with the material that is linear elastic? Conceptually, this is really a wonderful opportunity. Some of the folks, and especially I'm Italian, that are looking at seismic repair, rehabilitation, or renovation of historic structures are really now in Italy rethinking the issue of ductility, because of the level of damage that you would have in a building after a seismic event. So if we are really interested in sustainability in terms of having structures that last a long time and require low maintenance, this idea of dissipating energy with damage in a building may not be as sexy as we thought in the past. So, you know, think about that. That's a great topic of research. There is other topics that we don't cover in this code. Why? Because it's relatively new, even though some of us, including myself, spent 30 years of my academic life working on these materials. So I always pick this topic, the diaphragms. We don't have enough research to say we know how to design diaphragms, but it's coming. The other thing that there is a lot of excitement now is strut and tie design. It's not in the code yet, but there is a lot of efforts there because you can optimize the amount of reinforcement in the region. So very exciting topics, again, worth of research. So if you go to this code, you will see that some of the chapters are silent. If you go to chapter 12 and you compare it with 318, you will see there that it says not applicable. Okay, so be aware that there is some limitations. The issue of ductility, I'm not going to spend a lot of time here, and I don't want to be felt like I'm defensive here. But because there is no ductility in these materials, we have looked at the issue of deformability. So in other words, can you ensure the same level of safety in a structure that deforms so much that meets the reliability requirements of a ductile structure? It's a very interesting paradigm, and I invite the ones of you who are in the research arena to start thinking on these terms. And we have developed fee factors, so go back to your 318, the safety, the strength reduction factor that we use for safety, we have made sure that they provide, together with the load factors of ASCE 7, they provide the same level of reliability of steel reinforced structure. So this is very important. Safety is paramount. This is what we have to ensure. This is an obligation, is a moral obligation that we have as structural engineers. So this is really something that I'm going to mention here. I'm going to show you some numbers, and I'll let you think about it. Okay, so the resistant factors calibrated for both modes of failures, because we allow also the compression, concrete failure, which would be in 318 is kind of, wait, this is impossible. No, we allow it, but we calibrate the fee factors so that we have even a better reliability index, okay? And the same thing for shear. So the entire point, what is the fundamental reason? What is the background that we provide? Is really comparing the same level of deformability. What does the deformability gives us, and how do we compare it with the requirement of 318 in terms of strain? If you recall 318 says, in order for you to have a steel control failure, right, you have to have a strain in the reinforcement that at minimum is equal to 5,000 microstrain. We reach that with deformability, imposing a deflection that is 0.08 times the effective depth that will give you a strain in the reinforcement that exceeds the minimum of ACI 318. So this is, again, is a topic for very interesting discussion, and that's where you need to challenge your faculty members and say, does that really make sense? And so this, I invite you to have that debate. So I already mentioned this. I don't want to get into that. There was a question the other day when I made the presentation, this large displacements that these structures undergo before a failure are the expression of the potential failure, okay? But there is a great advantage. I know that Sergio in his youth was also interested in masonry. This is, for example, for out-of-plane situation, an incredible opportunity, because if the wall does not collapse, which obviously is what we hope, because the materials, the reinforcement remains linear elastic to failure, the structure rebounds. So in terms of repair rehabilitation, you only have to seal the cracks. You don't have a deformed structure. So now you have an opportunity to think in a different way, okay? So this is the beauty of it. Don't think, okay, even though today I look like an advocate of these materials, don't take my word. Think about differently. What can you do? And especially your generation that really has an important charge in life, that is to address the issue of sustainability. What can we do to attain that goal of making structures more durable, sustainable? And then there is potentially another advantage of these materials that I'm not going to mention really today, but is the fact that in terms of CO2 impact, this FRP is certainly less impactful than steel. So again, these are all things that need to be considered. You need to be aware of other differences, and this is shear strength, double action. I will show you some work that we're doing for the federal highway in the United States to address the issue of shear strength. The design procedures have to be slightly different, but fundamentally they remain the same. And because these materials have a lower module of elasticity, the issue of serviceability sometimes governs design. So deflection and crack control. Now you could argue why crack control if we don't have a durability issue. The crack control because of aesthetics. You don't want to walk around and see a structure that has a crack that is 6 to 10 millimeters wide that your hands will go through. People feel unsafe. So the aesthetics sometimes controls. This is maybe is the time that I mentioned in terms of deflection. Why deflections are an issue? Because you have a material, if it conforms to D7957, has a module of elasticity that is 47 GPa, 47 gigapascal. Steel is 200. Okay, the new generation bar is 60 GPa, but still, you could say, basically is less than 1/3 of that of steel. So you have to account for that. In terms of strength, we do much, much better. 2 times, 2.5 times the yield point of a grade 60 or 420 GPa bar, but in terms of modular elasticity, much less. In some instances, if you think masonry, for example, this could be a blessing. Okay, so not necessarily this is a negative thing. Maybe in pre-stressing, in terms of losses. So I think the beauty of engineering is to be creative with the materials that we have and be able to adjust the design and the way of thinking based on these materials. The other item that we're working on, even though this in my mind is the easiest one, is the fire resistance. Today, because we wanted the 440.1122 to be accepted by ICC, so it could be in the model code, because in the United States, if a document is not in the model code, it doesn't become the law of the land. The 50 states adopt IBC. They don't look at ACI. They adopt IBC, and IBC by reference adopts 318 and other ACI documents. So if this is not in IBC, then has basically no value. So in order for us to be compliant with the desires of the building officials, we said that as of now, this code is not applicable to structures that require fire-resistant ratings unless you can perform tests that can convince the building official. There is a lot of work going on now in this area. Actually, again, another challenge. Let me explain this, and then again, with your faculty, you can work it out. If I reach a temperature, let's say, of around 400 C, steel loses its modular elasticity, right? So now all of a sudden at 400 C, if there were to be a beam, well, let's say that this truss is a reinforced concrete truss, this truss will be on my head, right? Not because I destroy the steel, but because I lose the modular elasticity. In the case of an FRP, if I get to 400 C, what happens? Well, the resin will dissolve. That vinyl ester will disappear, not even burn, disappear. But the fibers will stay. So if you have the FRP anchored, then fire is not an issue. Just the opposite. You can reach probably 1,000 C before you see the failure of the structure. So there is a lot of work going on in tunneling work, because you know that in a tunnel, the fire issue are paramount. Even, I would argue, more important than a building. And so this is something that you can look at, provided that you have the continuity of the fibers, provided that you anchored your FRP, fire is not an issue. Okay, so very interesting topics. So let me go into some field application. I only pick a couple. There is many more, but I hope that these are of interest to you, and if there is questions, we can go over them. The one that you see, I'm just going to present the one in red. The first one is this bridge. If you're familiar with Florida and you know where Miami is, if you go north a little bit, you go in the county that is above Miami-Dade, you go into Broward. This is royal we, okay? So I myself do some work, but I'm not the only actor. But we built this bridge that is iconic to me, even though the spans are, ludicrous. Look, 26 feet, 16 feet, divided by 3, you have it in meters. It's not really exciting. But there is not a single pound of steel in that bridge, okay? This is the second one that we do in the state of Florida, but this is very dear to our heart because it's a bridge that was selected by the owner, in this case the city, as the solution for their case. The other one is more of a demonstration project. And here there is some innovation. The bridge deck is continuous with GFRP reinforcement. The other items that are of interest, so the cast in place flat slab is kind of a first. And the other item here, the precast panels and piles utilize carbon FRP, not GFRP, because in pre-stressing, the carbon is much more competitive in terms of performance. okay? Because you can stress the carbon at 70-75% of ultimate, so you can reach the same level of capacity that you have with the conventional 7-wire strands. And so that's why. But in this case, and I'll show you, we also did 3 piles using the glass, and we call that mild pre-stressing, because you can only attain 40% of ultimate because of a phenomenon called creep rupture. So this is an exciting thing. This is the project of casting piles with GFRP tendons. So these are number 4 rebars, so 12.5 millimeter in diameter, that we could have in a coil, so we could run them for the entire length of the bed, that is in feet 450. And so we could cast these piles, and we only pull the tendons to 40% of their ultimate because of this phenomenon of creep rupture. So very interesting for us, because we think that there is a future for this in the small piles, the one that are 12 inches by 12 inches, 24 feet long, so 8 meters, 25 centimeters in size, that we use for coastal construction. Just a number, Florida has 9,000 miles of seawalls, okay? And today they're all corroding, so if you want to do something that will last a little longer, then there is only this option. So these are the piles that are picked up. These are 18 by 18 inches, so they have to be the same size of the piles using carbon FRP, but again, we had quite some time in playing with them. So the items that you see sticking out are the bars that we pre-stressed, but then inside the pile, there is also a cage of unstressed reinforcement. So those were number 8 bars, so 25 millimeters in diameter. And this is another picture. This is the cap. So you can see it's a conventional construction, nothing different. Actually, the contractors love it because the weight of this material is 1/4. Okay? So from a sustainability perspective, imagine transportation cost, direction cost. So these are benefits that we maybe in this room don't much appreciate because we worry about design and research, but contractors love this stuff. Okay, so this again, the completing of the assembling of the form is the same thing. The casting, nothing special. Here you see the CFRP sheet piles that are driven as conventional piles, but you look at this, the connection to the cap is with GFRP L shapes. You see this is lighter in color. So there is a combination of reinforcement. And in the case of piles, now the Florida DOT allows you to use carbon FRP tendons and GFRP stirrups or ties. Okay, this sea of bars is just the deck, as you can see, 2 layers, so continuous flat slab. What we did immediately after, I'm not going to spend time on this, immediately after construction, on May 1st, 2021, we went out, we did a load test to get a sense of the stiffness of that flat slab. And look at this number. I'm only going to mention the natural frequency of this bridge. And then we went back a year after, and that's what we measure. So instead of 1881 initial, we are at 1863. So the change is basically insignificant. We're at 1%. There is no loss of stiffness. Now, the idea is to go back after 3 years and repeat this. Why? Because we think that there could be an interesting topic related to NDT in the future. If you want to monitor the changing stiffness of a structure, that could give you potentially an idea of the loss of stiffness and how much the cracking is developing. It's not necessarily a safety issue, but it could be a serviceability issue. The next one that I want to show you was also featured in a CI magazine. I assume that all of you are members of ACI. If not, I'm going to leave now. Okay, the students in particular is now I'm wearing my ACI hat. You know, membership is free, right? So how can you not be member? And I hope that Professor Alcocer, you know, makes this a requirement. When I teach, I don't teach very often, but I teach a class in reinforced concrete. I make it mandatory for my students. So, so if they don't show me that they are members, they cannot pass the class. So. This, you know, ACI doesn't make any money out of this, but I think is all the issue of get you engaged and involved. So this is, at one time, there is another very interesting application in Charleston in North Carolina. It's a different seawall, actually the replacement of the historic low battery seawall that uses more material. But when this was done in 2019, early 2019, it was the largest use of FRP. So this is a seawall at Flagler Beach. If you think of Florida, and if you know where Daytona Beach is, or little south of Jacksonville, this is the place. And this picture, I'll get to this later, shows you basically the job almost completed, okay? This is the beach, obviously you see the sea, and then the wall is inside here, is made with the technology called secant piles. You will see some pictures now, because the intention was to cover it with sand so that the users of the beach would not see it. And the entire purpose was to protect A1A, that is the old I-95 that connects Miami all the way to Boston, okay? So that's not us. was before we went, and this is the reason why you need a seawall, which sometimes one could think they are not really the best thing to do. Why do you want to build a road here? I mean, but it's already there. There is lots of people living here. So if we could rethink the way we do planning, I think we would not work this way. But now we're stuck with it. So when the hurricane came and washed away, this is not only dramatic damage, but imagine if you have to run away, or if you have to recover after a hurricane without the road. How can you go and help people? So this is really very important for many reasons. It's not just for pleasure. So this is the idea. The Florida DOT commissioned a study to a firm called McDonald in Tallahassee. They came up with the secant pile solution as the best solution, also economically. And then they already saw what we did at the University of Miami. We built a little bridge using this technology, and they liked the idea of using FRP reinforcement for the piles. And look at the amount of material that is used. I mean, you can see here, this is obviously in feet, but is close to 1 million linear feet of number 8 rebar. Okay, so this is the material being delivered to the site. What you see there in terms of bend shapes, this is for the cap. And this is the cages of these piles. I think it's beautiful stuff to see. By the way, they were doing it so fast that they had to break up the contract for the delivering of the grout, okay, or call it concrete, for the piles, because of the construction of the cages was going at the speed of light. If we were to redo this again, we don't need the nose. We use the nose in the project at UM because we were very concerned. I was very concerned by the fact that once you fill the hole with concrete, right, before you insert the cage, this material is lighter than steel, right? So the concern was, does it go in or it floats? So we wanted to have the nodes to make sure that we could pushing out, but you really don't need it. Actually, what happens is very interesting. If you go to a job site, you will see, in this case, excellent question. You can use either zip ties, but people don't like them. Now there is a company that makes a plastic gun. So you can shoot the same thing that you do with mild steel, but in some instances, some of the contractors love the plastic coated wire because it's commercially more available and totally inexpensive. So as long as it's plastic coated, it's okay. So the cages, again, very nice, very quick. This is the application. You see, the contractor was very smart in terms of the preparation of the guideway. So imagine a second pile is you cast the short piles, the one without reinforcement, and then you drill and you make the long piles next to it. So very interesting technique, very, very rapid. And then these are the piles going in, and you can see here, this is a beautiful picture of the cage being inserted. One of the reasons the people in that area loved it, because being overcast instead of driven, there was very minor noise, okay? So this is, I mean, this is certainly not an issue of vibration or anything like this. The buildings are far away. But certainly from a perspective of noise and not impacting the A1A that you see here in the background was certainly a positive thing. This is the cap that you can see being, so everything is in FRP. And remember this picture, keep that in mind, because I'm going to show you something exciting. So, oops, this is, what did I do? But I did hide them. Unbelievable, I made a mistake. Okay, what I want to tell you is just, I'm going to tell you a story. If you don't believe me, in the Professor Alcocer will have a copy of the slides. So the next 3 slides are most exciting. And I don't know, by mistake, I did hide them. Okay, this is the end of the construction, right? This is covered, you don't see it. You can go to the beach, you walk, and you're fine. Well, what happened in October of last year? A hurricane called Ian came by. And you know what that hurricane did? Remove 11 feet, okay, of sand. So now the wall is totally exposed. It's unbelievable. Okay, and all of a sudden you say, well, I really had very little to do. We did the right thing. We protected, there was not a single crack on the highway. Okay, so the design was done properly. And now the city of Flagler Beach, they announced it just a couple of weeks ago. This was part 1 of a project. Now they are going to extend the seawall to the rest of their jurisdiction. So very exciting. If you distribute, if it's of interest, just undo the next 3 slides, and they show this, a pity, but I forgot. This is my house under construction in the Bahamas. No, I wish. We have a very progressive community in Coral Gables, Florida. This medical doctor decided to build his summer home or winter home, whatever you want to call it, in the Bahamas, and decided to do it with FRP. Why? I did not show you the first of the field projects in that list. Can you guess what we're doing here that is unique? Apart from, okay, I mean, you see the sea is only less than 100 meters away. And so the issue of soil contamination with the seawater and all that is. But you know what we did? We used seawater for the mixtures. And why? Because chlorides have no effect. The chlorides depassivate the steel even when you have a pH of 12. The chlorides in concrete, provided that the concrete is durable, right? The only thing that you might worry is not the chlorides, is the sulfates that are in seawater. But that's another story when we discuss durability of concrete, not of reinforcement. So this is a project. So one of the things that we say in terms of sustainability, now you have the ability to use seawater. Would you use seawater in Mexico City? Is absurd, right? But you could use brackish water, or if there is a hurricane in Haiti, or if there is a hurricane in Cuba or in Puerto Rico, and you have to do emergency work, and you don't have access to fresh water, you can certainly do it with this. And by the way, this is my prediction. I will not be around maybe 30 years from now, but you will. Fresh water will be a commodity. You know, a few years ago, we were joking in Panama, and we were saying Panama will be much better off in closing the canal and bottling the water of the Gatun Lake, because it will be more profitable to the state of Panama to sell the fresh water than having the ships go through. Obviously, this is a joke, okay? It's not for real. But the point is, fresh water is very important to us. And the less water we use, the better off we are. You know, today I'm not going to talk about sustainability, but you know that we, our industry, our construction industry, and then there is a gentleman here from CEMEC, so he is the culprit, right? We use, no, I'm just kidding. They are a very progressive company. We as a construction industry, in general, everything included, we're responsible for more than a third of the CO2 emission. The concrete is responsible between 7 and 10%. So anything that we can do to mitigate this, and not only with better materials, but also saving water, could be an advantage. This is the FRP all over the place. You can see in the foundation. But the first picture was dedicated to Professor Alcocer because it's a masonry wall. So now, by the way, not only in the US, we have FRP allowed because of the 440 1122, but Appendix D in TMS 402, which is the building code for masonry structures, allows you to use GFRP bars. So it's both masonry as well as concrete. So this is, again, the concrete being poured, and you can see the beautiful sea next door. It's a beautiful place, by the way. They only invited me when they were under construction, but now that it's finished, they don't invite me anymore, but that's okay. I think we'll build another one. Current R&D, if you allow me just a few more slides to tell you what we're doing at the U. I just want to talk to you about 3 projects. The first one may be the most relevant to an ACI perspective. The second one as well, and the third one may be a little less, but very important now in the United States because the majority of the FRP goes in flat work. Trucks and trucks. Actually, if you come to the States and you go to Home Depot or Lowe's, you can buy the FRP sticks there, and the small contractors are using it very extensively because of the lightweight. Okay, so this is very interesting. So interface shear transfer with GFRP bars. Now the code, actually 318 itself, does not allow the use of the rebars as a transfer of shear when you have a connection. And this is really a big issue, especially in, not so much in buildings, but in the transportation infrastructure where you have a pre-stressed girder and then you have to pour a deck and you have to create the continuity and have composite action. So it would be ideal to continue with the stirrups so then they become the elements for shear transfer. We don't have enough experience, so there is a project funded by the transportation, let's say, agency, NCHRP, that allows us to look at that. So the entire idea is to look at what is the contribution of GFRP bars in terms of shear transfer, and then go back and then do some analytical work and optimization, and then hopefully correct both the AASHTO code as well as the ACI. The AASHTO is out there, actually is very unconservative, whereas ACI is on the other hand. I'm not going to show you that. I'm just going to show you some of the experimental results. So these are some of the specimen. Part 1, we have 18 specimens. These are called push-off, very common. In this case, you have 2 L's, right? You push down, you create a compression, but then you have this face here where you transfer the stresses by shear. So you have this heavily reinforced, in our case, in everybody's case, is steel, and then this has no reinforcement across the shear plane. In this case, you have 2 steel bars, the red ones, and in this case, you have 3 GFRP. So this is just the beginning of a study, and then our concept, and we think that by pure luck we were successful. We kind of demonstrated that there is an equivalence. 2 steel bars are equivalent to 3 GFRP bars in terms of performance. You will see why in a minute. The second part that I'm not going to report data on this, of this study is to create a joint here. So obviously, if you think of the girder is typically pre-stressed concrete with the bar sticking out, and then you pour the deck on top of it, so you have a cold joint. So if you cast the specimen only in one shot, you don't have a joint. So what we started doing, obviously, is to create this joint. So we do the first L, then we roughen this surface, and then we cast the other L, so we create a joint. And then we started playing with different amount of FRP. If you saw the first one had 3 bars, this is 1 bar. So this is an experimental study to initiate the work. This is the type of specimen that you see in the lab. It's fairly sizable. I mean, you need a forklift to pick it up. Measurements are obviously, as indicated here, LVDTs for the vertical, potentiometers for the horizontal, the opening of this crack. I'm not going to show you videos, otherwise I will stay here forever, but it's very interesting how this crack forms during the performance of the test. And obviously there is strain gauges inside the reinforcement to get a sense of how the stress, or better, the strain is distributed along the transverse reinforcement. This is, to me, is a very exciting slide, so take a second to think about it. Let's look at the color of the curve. So here, there's only the first 18 specimens, right? The red lines that end more or less here are the ones that are unreinforced. So let's say 200 kilonewton. The orange lines are the one with the steel, 2 bars. The blue lines are the one with GFRP. Look what happens after you reach the peak. Can you believe it? Look at this. The plateau is the same. And now all of a sudden, FRP gives you a pseudoplastic behavior. So this is very exciting, because now you don't design for the peak. You design for this, because once the crack occurs, you have to make sure that you hold the load. So all of a sudden, if I could generalize, but I'm not going to do this now, I'm saying that instead of 2 bars, if I have 3 bars, I can get the same capacity, not less, the same. So this is very exciting, okay? So this kind of dispels the notion that GFRP cannot be used for shear transfer, but more importantly, opens up a topic for great discussion among PhD students. Why that ductility? What creates that? And so we have our theories. I'm not going to divulge it now. It's in papers coming out. So these are the results of phase 1, and basically in words is what I told you. And then look at the pictures. We stop the test after a while, after you have all that deformation. But look at the steel specimen, the FRP specimen. If I delete the caption, would you know which one is which? They are identical, okay? And so you see that gap that was there to begin with obviously has become much smaller. The crack has opened up, but you don't see anything much different. The next one is a very interesting study. One of the limitations of these materials is related to the fact that bond is not as good as in the case of steel. Why? Well, if you think of the surface of a steel bar, you have the ribs, right? And then the mechanism of stress transfer is because of mechanical interlock. So the concrete, if you were to pull the bar, the steel rib will push against the concrete, and then obviously of the two, you eventually crush the concrete. Okay, either because you slip, or because you have cracking, or because the splitting governs, but you never destroy the steel. Well, in FRP, if you have a bar that, for example, provides you bond because of sand coating, well, the particles of sand will remain stuck to the concrete, and you it's almost like, if I were to give you an image, is the orange peel. Okay, it's like the peel remains stuck to the concrete and the orange comes out. So because of this, you have less bond. And even if you have ribs made out of FRP, the stiffness of the FRP is 47. Actually, is much less in the ribs because they are resin rich. So it's almost the same stiffness of the concrete. So you eventually can break, actually you typically break the ribs. So because of this, the development length of a bar is much longer. To us, doesn't make a difference. But when you're in design, oh boy, that's not pretty, right? Especially for steel conjecture. So we are running there's a lot of work going on to see if we can, with better science, limit the development length. Also because the data, actually, our great Carol Schild at ACI was the, let's say, the person who developed the provisions of the code in the 440 document. But the data that she used, obviously, this is more than a decade old, when the old generation bars were used, and now we're looking at the new generation. So this, and she's part of this project. So in here we use beams that are maybe, I cannot remember exactly, but maybe 6 meters long. I have a next slide. And we use a lot of stuff to consider the parameters that can affect this: the concrete strength, the GFRP diameter, the clear cover, the confinement offered by the stirrups, and the splice length. This project is done together with the ACI colleague, Brahim Ben-Mokrain, at Sherbrooke University. And our student, actually, he does all the testing because he has plenty money like you have here in Mexico City. And we send the students over there during the summer, not in the winter. Actually, we should send them in the winter because in Sherbrooke, there's not much to do during the winter time. So anyhow, so that's what we do, and then the data that we collect are indicated here, and then we process them. I just want to show you the best thing that we're doing, which I think is unique because many have done this type of test, is we stick this tiny little potentiometer at the end of the rebar when we are splicing the bars, so we can measure the slip. And then you can see here how the bar or the potentiometer is protected, so you can pour the concrete. And the beauty of this, not only you measure the slip, but you do not affect the bond of the bar, because when you apply a strain gauge, you have to, clean the surface and make it flat. So you kind of decrease the amount of surface that is really there for bond. So these data are becoming very useful because we measure slip. Okay, so I just want to show you one case, okay, where we test specimens that have bars that are, number 8, 25 millimeters. The 25 millimeter is the cover, and the bar is a number 5, is an M16. These are sand coated, and then we test three splice lengths, 40 diameters, 60 diameters, 80 diameters, and obviously the bar one is continuous. By the way, if we were to use development length for a splice without, any factors, any safety factors there, the number of diameters would be close to 150. So we're much lower than that, just to see the effect and that. And so look at this, these ratios. So if you look at the experimental, this is using the material property tested in the laboratory, and you come up with a prediction. And obviously, if you have the continuous, basically, you match exactly what you have. And then in the other cases, you are at 46, 61, 72%. But once you put the phi in front of your MN, okay, so if you think in terms of design, if you have a continuous one, you are at, 2.2 times your design need. And then if you, even with 40 diameters, which is 1/3 of what the code requires, you meet the need. I'm not arguing. I'm not saying that this is what we should be doing, but you can see the effect. And this is the failure is really for slippage, okay, rather than anything else. There is very little, cracking due to the presence of the bars. One thing that I'm going to ask you to think about, if, again, Professor Alcocer distributed the slides, if you have some slip as we saw it, why do not have a degradation of stiffness? We're still thinking about it. So here we have 3 beams, right, that I'm plotting. And then here I have the mid-span deflection, and here I have the, the load that I'm applying. So this is the continuous one, right? You can see they all crack more or less at the same point. By the way, these beams are notched, so we control the location of the notches where the end of the splices is, because we need to make sure that we understand how the crack location affects, capacity. So they all crack at the same, and then they proceed with the same stiffness. Even the green one that, has a capacity that is less than half of the continuous does not have a degradation of stiffness. Honestly, I just don't understand it. So help us out, okay? We're still working it. We have many more beams to look at, but the performance is the same. So very interesting that, so this is your FMN, as I said, if you were to be designing, even with 40 dB, apparently you would not kill anybody, but obviously with 60 you would be better, with 80 better, and then if this is where you are with the code, continuous one, you will do much better. But this is an interesting issue. Why don't I have degradation of stiffness if my bars do slip? So this is something we cannot figure out. What is missing here, which is a topic for great PhD, is doing cycling testing. Because if I do cycling testing and I have slip, boy, that is going to be permanent. So you have a degradation. You must have degradation of stiffness. We don't understand why it doesn't show here. This is a slide that is a little puzzling for you, but I just want to show it to you that if one were to compute the average bond stress, that really means nothing because we have no idea what is the distribution. And if we compute it according to code, we're right there. Okay, so with the 40, 60, and 80 development length, the 80 would be here, the 60 and the 40, we develop the same bond strength that the code seems to indicate. So this is very comforting. Final item, and then I'll get to the end, and maybe hopefully there will be questions. This is less interesting to you, I imagine, because this is almost like a trivial topic, right? Who wants to do slabs on ground? But, if you think in terms of amount of concrete, and if I look at my colleagues from CEMEX, a lot of concrete goes in slabs on ground. And therefore, this is an area that, is worth looking at. Why? Because we want to make sure that you don't have to replace those slabs on ground. And if nothing else, make them more efficient. So we're looking at one issue that is kind of, in the scheme of things, trivial, is the early age cracking behavior. So is the effect of plastic shrinkage. And I'll give you the final part of it, and that's why I kind of take away the thunder, if you wish. If you want to address the issue of plastic shrinkage, the reinforcement does nothing. Would you be steel or FRP, it doesn't make a difference. And the reason is because you don't develop enough bond strength. When the concrete is in its plastic state, the bar is there just for fun. It's doing absolutely nothing. Is when you go into dry shrinkage, that is a different story. But the work that I'm showing you, and so we wanted to do this because you might not know this, but I think it's a nice, if you want to do some work related to code. Chapter 1 of the building code, the model code, sorry, says that if a technology or a material system is not mentioned in the code, you can still use it, provided that you have what we call an ESR, an evaluation service report. So if you have a report that shows compliance with the intent of the code, compliance with the intent of the code, it cannot meet the code because it's something different, right? But if you show compliance with the intent, then the building official is compelled to use it. So how do we address this compliance? There is an organization that is a subsidiary of ICC called ICCES. And ICCES develops acceptance criteria for new technologies. And one of the acceptance criteria is for the use of FRP reinforcement for crack control in slabs. And therefore, we wanted to make sure that the tests that are prescribed in this AC521, this is the name or the acronym of this acceptance criteria, make sense. And what we are saying is, you know, it doesn't matter how much reinforcement you put it there, it's going to do whatever the steel does, because both don't really help, you know, in the plastic condition. So this is the work that we monitor. We have many slabs going on in our area. This is one in a beautiful part of South Florida. Here we are in the Keys, and then you can see the reinforcement here. You see chair. The workers love it. And you know why they love it? You don't see it here, but one of my PhD students who's monitoring this took beautiful videos. You see how closely tight is the reinforcement? If you have number 3 steel bars and these guys walk on it and there is no other way, they don't see what the reinforcement is. And even if they did, the foot doesn't fit this hole. They step on it, they bend it, and the reinforcement goes against the floor. What good does it do for, you know, drying shrinkage? Nothing. But if it's FRP, it bounces back. So perfectly elastic to failure could be a great attribute. Okay, so we do this work to, in a sense, if you wish, to validate this ICCS AC521. And so what we have done, I'll fly through this because perhaps is not of dramatic interest here. We do a lot of material work at the University of Miami. Not only, one of the reasons is because I have not seen your lab, but I imagine it's fabulous, and we don't have really a structures lab. So we are confined to do more material work, and then we go to colleagues to do the structure work. So we took a modified C1579. This is an ASTM standard for FRC, fiber reinforced concrete, and we modified to look at the viability of using GFRP bars that could be made of glass FRP or basalt FRP. There is a lot of basalt coming up now as an alternative to glass. The Europeans love it because they claim it's even more benign to the environment. In terms of properties, very similar to glass. We don't have yet a manufacturer of basalt fibers in the United States. We had one, Mafic, now is out of business for a while. So there is not really abundance of basalt. The basalt that we use comes from a part of the world that is little under stress, meaning Ukraine and Russia. So it's a little bit of difficult, but once things settle there, or we start manufacturing basalt in this part of the hemisphere, I think you will see that fiber coming up. I think it's very exciting, and it's certainly an alternative to glass. So we test this with bars or meshes, and then we need to make sure that there is some cracking, because if there is no cracking, you cannot establish the equivalency. Remember, we want to show that the FRP is equivalent to the steel. And then particularly the welded wire meshes that are commonly used for slabs on ground. So we create an environment inside this chamber that looks like this that is very aggressive. In fact, we even warm up the aggregate and the water to make sure that there is a very high heat of hydration in the beginning, and that expansion that we have will then cool off and cause the cracking. So this is some of the tests. I'm just going to fly through this because I don't think also in terms of ability for you to see it. We just got a paper published as I was in already Mexico, and actually is a collaboration with our colleagues on the West Coast, not the West Coast of Florida, but California, where they do all the analytical work to generate diagrams like this. So we have measured with a penetration test the setting time, and fundamentally what we're saying is that the shrinkage cracking or the plastic shrinkage cracking is a function of many things, but the contribution of the reinforcement is practically zero, because before the concrete sets, that takes approximately between 3 to 4 hours, the level of bond that you have is insignificant. So we monitor these cracks, we come up with different methodologies to look at them, and then we measure them. We have also imaging tools that allow us to see where they are. So I think it's exciting, but we are more on the material side. But the point here that I wanted to make is research has to cover the aspects of structural engineering that are related to safety, but also don't forget that there is also another world that has to do with the way that we use materials that have to be economical to society. And this is, I think, a good example. In order for us to determine that or understand the reason why of this performance during the plastic shrinkage, we run these tests that we call early age bond tests. And you can see it's very similar to a pull-out test that you do according to the standard, but obviously the concrete has not yet hardened. The concrete has not gone through the full hydration process, and so you determine the capacity of the bond and you determine that you really don't have any bond, and therefore if you don't have any bond, the reinforcement is there for nothing. So we do the modeling is done by John Bolander in California, incredible guy that is using, that has really modified all the work that he has done in FRC to match the needs that we have in FRP, and very exciting. And the modeling that we do, the numerical simulation, even related to temperature, look at all the specimens are inside this fuse. So I think that now we are at the position where we can generalize the finding that we have. So I'm down to the conclusions, and I only have one page, okay? And I think we have a compelling case to say that as a technical community, we should look at these new materials. If nothing else, for structures that are exposed to aggressive environments. There could be other reasons. For example, there was a question yesterday, if I'm in the precast business, why would I use this? Well, imagine what it means to you if you make panels, and if you now can cut down the thickness of the cover. Instead of 1.5 inches, okay, it's 39 millimeters, whatever it is, if you could go down to 0.75 of an inch, I need enough cover for bond. I don't need it for durability. Now, you know what it means to shave 3/4 of an inch on each side of a panel? On a panel that is 6 inches wide? Do you know what it means in terms of transportation costs? So this is a compelling reason. It has nothing to do with an environment where you are in an aggressive situation. As importantly, not more importantly, GFRP is an ideal material in terms of non-transmitting, in terms of non-conductivity. Okay, so all of a sudden, your thermal bridges become inexistent. So if you have a panel and you have a sandwich construction, a face of concrete, polystyrene, concrete, now the ties that connect the two panels could be made out of FRP. If they are made of FRP, you don't have any thermal bridging. So again, these are compelling reasons in industries that have nothing to do with the, let's say, corrosion resistance. So I think this is, even though today I did not mention the saving of fresh water is exciting, natural resources, what the heck I'm talking about? Recycle concrete as aggregate. Today, very difficult to be used because of chloride contamination. You take down a bridge, you crush the concrete. What is the only use that you can make? A base material. Why? Because it's chloride contaminated. You cannot put it inside, a mixture. So now, all of a sudden, chlorides, we don't care. You can be as high as you want. So this natural resource, sea sand, and so on and so forth. Actually, I read this morning, as I was waiting for the plane, there was a short report that Taiwan and Vietnam are very nervous about the fact that China is building an airstrip in the South China Sea, on an island that is contested by the three nations. Do you know what materials they are using there? FRP. Why? Because there is no fresh water, and the sand that they get it directly from the sea without washing it. Okay, you can't use steel. So again, I'm not arguing that you will do this in Mexico City, but all I'm saying is this opens up a new host of applications that are exciting. The issue of elimination of corrosion, reduction of maintenance costs, service life increase, and don't remember the stuff that we engineers may not be really keen about, but what are the issues related to constructability? Would that be transportation or productivity? Stefan Steputat, who's the PhD student who follow very closely the Flagler Beach seawall, was there for 3 months monitoring productivity. 55% increase. Why? Because we were not breaking the back of the workers. So that's another reason, that the unions in New York City love it. Why? Because there will be less injuries in the work. So I'm not saying that this is the reason for using these materials, but I'm saying it could be. These are what I say peripheral reasons that make technology more viable. I think our obligation as researchers is to make sure that we address all these aspects, starting with safety, that is paramount, but don't disregard the other aspect. Obviously today, I only gave you the good things about this material, and then maybe next time when I visit you, we'll discuss the other items. But I think, in my mind, if you don't have the motivation and the excitement, you don't start from the negatives, you start from the positive. And I think with this, we're done. Thank you very much. Can I take questions?
Sure.
Do I have any questions?
Question?
This is by the way, this is a dock built in Miami, Cat 5 resistant, made solely on FRP, including the piles. The piles are not PC, they are RC, and the water used by the precaster comes from Biscayne Bay. So we loaded up a truck. I mean, they thought we were crazy because the precaster core slab did not really very much like. The drawback of this, I mean, we all love to use seawater, but if you are the owner of a ready-mix truck, you might not be very excited to put salt water inside the truck. So questions, remarks, comments, maybe.
¿Alguna pregunta?
En español también, ¿no?
O en
Yo la
italiano.
entiendo y puede
italiano.
ser que otro puede
En italiano
traducirlo.
también.
En italiano, sí.
We had about 80 people connected online. We have some questions, Tony.
Okay. All right.
Oscar Minor asked, what is the cost of GFRP construction compared to typical steel? Is there a trend on the use of these? And if you think that's the cost is going to go down?
Okay. With the premise that I'm not the best guy to talk about cost. We researchers don't worry about that, but this is a question that comes to us very often. Historically, GFRP has been more expensive than black steel. There is studies, and they are publicly available in publications, where, for example, in Kansas City, they look at the construction of a bridge where half of it, the 2 lanes were done with GFRP, the other 2 lanes with steel. And the implications in terms of cost in those days was an increment of 4%. 4. Okay. But today, so this was probably 10 to 15 years ago. Today, because of the and especially last year, the increase, I don't know Mexico, I can speak only of the US, the increasing cost of the post-COVID situation for steel, GFRP was cheaper on the first cost basis than steel. Today, now that price of steel is stabilized, again, I speak about the US situation, I don't know Mexico, it is less expensive than epoxy coated steel. And for, black steel, it's, very similar. The sticks that you can buy at Home Depot or Lowe's, so the small diameter bar, number 3 and number 4, are cheaper than black steel. So I think the issue of cost is a tricky question, and the answer is as tricky. So I don't know if I responded, but again, it's a market issue, and sometimes there is a fluctuation.
Thank you. ¿Alguna pregunta? Some question? Rubén. Por favor.
So I didn't know there's people online. Great.
Yeah, there are 80 people, plus about 20, 30 people.
So I should have been more careful in the things that I said.
Well, you did your speech. Rubén.
Thank you for your presentation. I would like to ask about the combination of these kind of bars with glass fiber.
With the short fibers?
Yes.
Beautiful question. Actually, this is something that there is interesting research going on for the reason that is related to the lower modular elasticity of the bars. So the short fibers will give you the opportunity to better control cracking.
Yes.
So it's interesting. It's certainly something that the DOTs would be looking at. We have removed in ACI the requirements for crack width, okay? It goes back to maybe 2 decades ago. And the only requirement is the distance between reinforcement. And actually a great colleague by the name of Robert Frosch came up with an equivalency. But if you design according to AASHTO, which is the code for the transportation infrastructure, we still look at the width of a crack. So even though you could argue a large crack doesn't bother me from a durability standpoint, AASHTO specs still limit the crack width. The only way to take care of it, or one way to take care of it, is with the short fibers. So certainly this is an exciting topic.
Thank you. ¿Alguna otra pregunta? Diana.
Professor Nanni, thank you for your presentation. Can you tell us more about the procedures to study or to monitor the structural health of these kind of structures?
That's a loaded question. It's a difficult question. Actually, there is a project that we are running with Florida International University, and they are the prime. It's an FHWA project that is interested in determining the monitoring of these structures. Actually, the project deals with 2 types, externally bonded FRP, so repair rehabilitation, so where the FRP is applied as sheets, as near surface mounted bars, and that's easy, okay, because it's outside. With the internal FRP, boy, it's a hard thing because these materials are not magnetic. The methodology that you have to locate the steel bars may not work well with these systems. So the work that we are doing seems to indicate that with a little bit of experience, the contribution of the manufacturers, some of NDT equipment, it may be possible. But I would say that this is one of the weaknesses that I've not mentioned. We ourselves discovered the issue, and I'll tell you a case in the other bridge that was built only with GFRP bars. We had to, after the construction of the deck, we had to insert GFRP bars to tie the railings, okay? The railings had to be cast in place, but they had to be tied to the deck, right? So we had to go in and drill holes to put the bars in. well, where are the bars in the deck? So you think you know because you look at the drawings, but the contractor may not have placed them in the right place. So these are issues. So you have mentioned one of the weaknesses. I'm not going to mention the others, so see if you can guess. But certainly it's another great area of research, but you need the help perhaps of industry, the people who develop equipment. But excellent question.
Thank you. There are several questions online. There is one that, the question is in Spanish. If there is an intent...
No, en español, por favor. So I can, even though I did not have tequila.
Perfect, but this I'm going to answer it for you anyway.
Okay.
Existe una iniciativa para reglamentar esto en México. Yo,
Sí.
en la nueva norma de concreto que se publicará en mediados de septiembre, tenemos en el capítulo 15, la sección 15.10, un apartado especial para el uso de este tipo de fibras y poderse utilizar en estructuras de concreto. Lo estamos limitando en este momento a estructuras que nosotros denominamos de ductilidad baja, para estructuras relativamente pequeñas, que denominamos del grupo B2, pequeñas o no importantes como escuelas, hospitales, y únicamente para aquellos elementos estructurales que no resisten sismo, no para los elementos estructurales que van a resistir el sismo. Entonces, nos referimos a la publicación 440 para que se puedan utilizar para fines de diseño. Ese es un primer tema. Segundo, se mencionó el tema de las losas, de slabs on ground.
Sí.
Tenemos un apéndice, el apéndice D, es un nuevo apéndice para el diseño de losas sobre terreno, que es un tema que se había visto de interés en México porque no teníamos criterios de diseño y de construcción, entonces incluyó un apéndice. Y también otro apéndice, C, que es responsabilidad de Arturo Gaitán, que es un apéndice sobre sustentabilidad, en donde establecemos las métricas que hay que seguir para que las estructuras sean sustentables, independientemente que se utilice acero de refuerzo metálico o no metálico. Esa es en la norma de concreto. Y en la norma, también nueva norma, de evaluación y rehabilitación, en la sección 9, no me acuerdo cuál, 9 punto tantos, permitimos el FRP para rehabilitar estructuras por sismo, ya sea en forma de bandas o en forma de wrapping, ¿no? Todas las bandas. Entonces, tenemos el uso de estos materiales compuestos ya incluido en las normas que saldrán en 15 días, un mes, una cosa del estilo.
Wonderful. So I came in late.
No, you're fine. Because we need to solve the other problems.
Yeah, absolutely. No, this is a very exciting topic, and that was a great question and a great answer.
Hay aquí varias preguntas y comentarios.
Sí.
Uno es, si es, es un comentario que este sería un material que pudiera ser efectivo en las inversiones públicas, que permiten un costo de inversión mayor, pero disminuyen los mantenimientos y por tanto a lo largo de la vida útil hay una reducción en el costo total.
But can I comment on this?
Sure.
You know, until we get to the point that new technology is economically viable, even on a first cost basis, we cannot really have implementation. And the reason to me is very simple. If the city of Mexico City, needs 2 bridges, and you say, I'm going to build you one at the cost of 2, and it's going to last for 120 years, nobody could say yes, because I need 2 bridges, I don't need one. So I think the objective, and I think it's in the making, when we will be through the scaling up of these material systems, they will have to be more efficient in terms of first cost. In fact, one of the projects that I did not show you because is in Saudi Arabia and is really a flood canal, 20 kilometers, until last year, the largest application of FRP in the world. The savings on a first cost basis was 21% compared to epoxy coated steel. So let me repeat it, 21% on a first cost. And not me, this is the contractor coming up with the value. So I think that is where the excitement is. At least be equal in terms of first cost, if not better. And I think the advantage is there. The reason for the savings was primarily the transportation cost. And, for example, I have a table that comes from them, not myself, where the cost of equipment, crane, was zero. Zero in the case of FRP, because they could offload by hand from the truck. So I think the answer to that question is we need to work on it. Otherwise, deployment will not ever occur. It's a different story for repair rehabilitation. For repair rehabilitation, even the cost is higher, the downtime is the key.
Right.
You know, actually in the 90s, when we did the first jobs of repair in buildings, we would do repairs, and we did them also as university, overnight in buildings during weekends. So now, then, who cares if the cost of the FRP, carbon FRP, is 10 times whatever other technology is? Nobody will know that you're in. So I think repair and new construction are two different items. But excellent point.
Karen, por favor. Oh, by the way, perdón un segundo. Relacionado con el canal que menciona el profesor, hay un artículo en Concreto International.
Yeah.
About, what, 2 years ago, perhaps? And that explica cómo se construyó y cómo se diseñó, por qué estén interesados. Y ahí se hacen miembros del ACI de manera forzosa, y entonces me va a reducir la cuota como miembro. I don't think so. Karen.
No reducir, duplicar. Duplicar la quota.
Karen, adelante.
Grazie, professor, per la sua presentazione. The question is about the water from the sea. Needs something to treatment for using?
No, actually this, again, another great question. There is no impact of seawater on the GFRP. The impact could be on the concrete itself, particularly, and in this area, I think the colleagues in China are ahead of us because they are conducting, many studies. And if you look at the literature today in seawater concrete, you will see a lot of literature coming from China. There is two issues that you have to look at when you think of the concrete. One is related to the durability, not so much for the chlorides, but potentially the sulfates that are in the seawater. And the other one is the impact on the workability. The presence of chloride may speed up the setting of the concrete. So you might have to play with some of their mixtures to control it. So these are the two things. But from a perspective of the reinforcement, we don't have any issue. But again, that doesn't mean that you can go out and just use the conventional concrete. You have to be, even though, if you come to Florida and if you go down from Miami down to the Keys, some of the old bridges were built with seawater concrete. So we have not invented anything new. We're simply saying, hey, now you have a reinforcement that is not affected by the chlorides.
Oh, very interesting. Una pregunta sobre si las zonas que mencionó ABC se refería a México, Estados Unidos, permítame contestarla. No se refería a zonas, sino al uso del edificio, categorías del edificio, que hay A, B, C, D, y que tienen una relación en cuanto a la zonificación, dónde se va a construir y el tipo de ductilidad o de tallado dúctil que se requiere. Entonces es un concepto distinto propiamente de las zonas sísmicas. Déjenme ver, que si podemos dar una copia de las diapositivas, amablemente ha permitido que así sea. ¿Qué tan aceptable sería usar en edificaciones con alto grado de irregularidad, torsional problems and irregularities? ¿Hasta qué número de niveles? ¿Si hay alguna receta o alguna
receta? No hay recetas. Okay, so let me speak to another weakness that is kind of implied, I think, in this question. And some questions are tricky, and this is one of them. Why is the Jazan Canal, providing a saving of 21% on first construction cost? Because all the bars were straight. Where is the weakness of this material? One of the weaknesses is the bend shapes. For two reasons. One, because the strength is degraded when you bend the bar, okay? But this, we can live with this because the strength is never an issue for FRP. If there is an issue, is the E, the motive elasticity. But there is another dramatic reason. Today, the bend shapes are done by the pultruders. So the same companies that make the straight bars. So if you come to the United States and you say, I'm building a bridge, the bridge that you saw, in that case, the bars came, I believe, from Owens Corning. So they were made in North Carolina. If you screw up in the number of stirrups, you have to call the fabricator and say, oh, by the way, I need 12 more. And do you think that the fabricator will sell you 12 bars? Because there is a special shape, it was a special order. Say, oh yeah, we'll sell you. I mean, the cost is probably 3 times what you paid before. And this is really nothing, the cost of, who cares about 10 stirrups? But you have to wait 3 months. And now you're in the middle of the project, so what are you going to do? So this is the weakness that we still rely on the pultruders to provide the bend shapes. Do we have a solution to it? Yes, and this is a great research topic. If you use a thermoset resin, like vinyl ester or epoxy, once the resin polymerizes, you're stuck, okay? There's nothing you can do. But if you use a thermoplastic, that's a different story. So now we are working with liquid acrylic, in particular, well, that's our work, but others are using different thermoplastic. Why liquid acrylic? Because it's a 2-component, like vinyl ester or epoxy. So you can use the same bath to wet the fibers at the pultrusion house. If you think in terms of pultrusion, you have toes of fibers that go inside the bath like a bathtub. They come out, they go inside the die, you squeeze the excess resin and you shape it, right? So now using liquid acrylic is like using vinyl ester, but what is the advantage? That you can use the same equipment for bending the steel bar, provided that you do 2 things. You have to warm it up before it enters the bending machine, and you have to twist it, because if you don't twist it when you bend it, the fibers that are on the inside of the diameter will buckle, right? Because they want to become shorter. So this is coming. A year from now, we'll have addressed that issue. But this is a topic of great interest, because have we come up with the right resin? You see, if there is a segment of our industry, in my mind, that has not step up to the plate, is the resin manufacturers. The fibers people are all excited and they look at this. But resin people, they already sell enough resin. But we need them, because the resin has a fundamental function. It's not only for the TG, it's not only for reliability and so on and so forth and protection, but it's also for this reason. So our dream is to be able to have the bars not bent by the pultruder, but bent by the fabricator with the same value chain that you have today for steel. So in our case, you call up somebody in Jacksonville and you say, I need 10 stirrups. They have the FRP number 3 or number 4 in a reel, and they can bend it. Well, obviously it will cost you a little more, because you have to heat it up, twist it, okay. But then, I mean, here the sky is the limit. You could have resin that you can UV cure. Okay, so anyhow, technology could go to the speed of light if there is a driver, and I think we are creating the driver now. So these are all weaknesses that I think can be addressed.
3 more questions.
Well, so we'll stay here till 2?
More or less.
Okay, go.
The first one is there a special consideration of lab equipment for testing these materials?
Yes. Okay. Special equipment, okay, for some tests. Some are trivial. For example, if you want to measure the fiber content, that is one of the requirements of the ASTM D7957, you have to have an oven, so then you can put coupons of GFRP, you do the burnout, and then you measure. You have to have a scale of high precision, so it's trivial. The other thing that is trivial, but you need to know what you're doing, if you're doing a tensile test, you have to be able to grip it. Now, if you use the conventional devices, would they be hydraulic or wedges that you use for steel, you're going to crush the FRP bar and you're going to get nothing out of it. So you have to provide a steel pipe, an expensive material inside. We use expensive cement, and then you attain the result. So in that sense, you don't need anything special. There is some special equipment if you want to use, for example, the level of polymerization of the resin and something like this. But I would say that any lab, particularly university labs that have all the equipment, if it's not in your conventional lab, the chemistry people have it. And so I would say no. You only need to be cognizant that this is not steel, and you have to treat it differently. But other than that, we test it day and night. I mean, at UM, because it's part of the service, and we test bars from all over the world. So if the person asking the question, they should not go to UNAM, they should come to
Miami. Okay, and then you lower the cost
of course.
membership. And la última pregunta es si hay proveedores de este tipo de barras en México.
Oh boy.
Y la respuesta es, ¿no sabes?
I'm going to pass on this because
El presidente nunca puede decir que no
yo
sabe.
sé, pero quiero no responder.
O sea, ¿sí hay fabricantes?
No hay fabricantes, hay distribuidores.
Distribuidores. Sí, pero fabricantes no hay, ¿verdad?
No hay fabricantes. Que yo sepa.
Bueno, no sé si hay alguna otra pregunta, algún otro comentario. Si no, pues muchísimas gracias, Tony, aquí en nombre del Instituto de Ingeniería, que entregamos este diploma que dice por haber impartido la conferencia Concreto con refuerzo no metálico, materiales poliméricos de fibra de vidrio, reglamentos de diseño, aplicaciones en campo, investigación y desarrollo, el 17 de agosto de 2023, Salón de Seminarios Emilio Rosenbluth, firmado por nuestra directora, la doctora Rosa María Ramírez.
Gracias.
Y un pequeño recuerdo para que
fantástico.
nos recuerdes cuando tomes un café, un té,
Ok.
o mucho tequila.
Tequila aquí.
un copa de-
Vamos a tomar una foto, sí.
Sí, claro.
Así veo. Arturo, come in the middle. You have to give me this, otherwise. Yeah. Así que hay. Perfecto, gracias. Y gracias a todos.
Pues muchísimas gracias por haber asistido a esta presentación y estaremos pidiéndoles que asistan en otras próximas reuniones. Muchas gracias.